There's an awful lot of level 2 maths that you need to be able to do in your biology exam. So here are most of those skills that you need to be able to carry out. First of all, the mean. You add the repeats together. Now do not just divide that by the number of repeats. Press equals first, otherwise you'll divide the last number by the number of repeats. So add them up, press equals, divide by the number of repeats. So we've got 3 repeats, 5, 7 and 5, add them up, press equals, that gives 17, divide by the number of repeats, gives 5.67. For some reason the editing on this piece of software has taken the O over there. This is the ratio. You could be asked to calculate the ratio. I've only seen this a couple of times, but it has been asked before. So let's say the mean length of a person's arm or people's arms is 0.3 metres and the mean length of people's legs is 1 metre. So the ratio is 1 to 0.3. But again, we want it something to 1. So divide both numbers by the smaller number. So 1 divided by 0.3 is 3.33. 0.3 divided by 0.3 is 1. So we've got a ratio of 3.33 to 1. Percentage. So percentage is the value divided by the total times by 100. So let's say 60 students smoked out of 150 who study AS biology. So in this case, the value, we wanted to work out the percentage of students that smoked. So the value is 60 divided by the total number of students, which is 150, gives 0.4, times by 100, so 40% of the students smoked. You could be asked to convert decimals to percentages. So I think this is quite straightforward, but some people find it quite difficult. If you've got a decimal, just times it by 100 and that gives you the percentage. Or if you need to do it the other way around, if you've got a percentage and you want to create a decimal, you divide it by 100 and it gives you the decimal. Percentage change could be quite tricky, but it's quite a common calculation that you could be asked to do. When doing percentage change, you need to, the most difficult thing is knowing what the original value is. If you're just doing a general percentage change, then read the graph from left to right, or read a table from top to bottom, with the left-hand number, the one most to the left being the original value, and the one most to the right not being the original value. If you're working out percentage increase, then the lower number is the original. If you're working out percentage decrease, then the higher number is the original value. So it's difference divided by original times by 100. So we want to work out the percentage change between 1982 and 1999. So let's look at 1982. Read up from 1982, read across, gives us a value of 0.8. 1999. Read up from 1999, read across gives you a value of 5.8. So the difference is 5.8 minus 0.8, which gives us a value of 5. Divide by the original value. As I said, the original value is the one that's most to the left on the graph. So this is more to the left than this one. So this is the original value. 5 divided by 0.8 is 6.25. Times by 100 is 625%. Now some people think they've gone wrong and try and do something completely different, but a number that's bigger than 100 means that the number has increased. You've got a percentage increase, so that is actually correct. You've got a 625% change, showing that this number is bigger than this number because it's a bigger than 100% increase. Rate of change. Now this is similar to an enzyme rate of reaction or rate of transpiration. A rate of change is something divided by the time taken. So a rate is something per unit time. Rate of change, so it's the difference divided by the time taken. The time could be in seconds, minutes, or in this case, hours. So the difference in the first 10 minutes. So difference, read up from 10 minutes, read across. So we've got 10.8, it's gone from 0. So 10.8 minus 0, so the difference is 10.8. and it's in arbitrary units. So 10.8 divided by the time taken, which was 10 hours, so the difference is 1.08 arbitrary units per minute. This time we're going to do a rate of change using a table. Perhaps a little bit more tricky. We're going to use the left ventricle and we're going to look at the rate of increase in pressure in the first 0.3 seconds. So the pressure before the ventricle contracts is 0.3. The pressure after the ventricle is fully contracted is 15.3 kilopascals. So we want to know the rate of change, how quickly the pressure increases as the ventricle contracts. So the difference is the lowest, so the biggest number take away the lowest number. So 15.3 minus 0.3. So 15, that gives us 15 kilopascals. That's how much the pressure has increased by, divided by the time taken. So this is 0.3, where you got the highest pressure, and 0 times 0, where you got the lowest pressure. So 15 divided by 0.3, which is the time, which gives us 50 kilopascals per second. So the pressure is increasing at a rate of 50 kilopascals per second when the ventricles contracting. Now you won't be asked to calculate a logarithm, but as you've seen on questions before, you might be asked to know what one is. So they're often used to plot bacterial growth curves. That's when they're mostly used. But it just simply allows a large scale to fit on the same graph. So the reason you use it for bacterial cells is at the beginning, if you want to know in a fermenter, for example, how many bacterial cells you've got, right at the beginning you could have a very small number, right at the earliest times. You could have 20 bacterial cells to start off with. But after a few hours you could have as many as 10 million or billions of different bacterial cells. Now that'd be very difficult to fit it on one graph if you use 20 at one end and 10 million at the other. You need a huge sheet of graph paper. So to create it into a logarithm, and then you can fit it on the same scale. And here's the past paper question you might have seen before. You could be asked to calculate the circumference of a circle, okay, or a sphere. So circumference of a circle is 2 pi r. You could be asked to calculate the area, surface area, or the volume of a sort of a cuboid or a cube. So here is the formula. Volume is the length times the width times the height, and the surface area is 2 times the width times the height plus the length times the width plus the length times the height. Sometimes in an answer you might be asked to use the correct unit, calculate the correct units to use. So in this example here, if you're trying to do a rate of reaction, so rate is in this case concentration divided by time. So the rate of reaction for this point here, so it would be the concentration divided by the time, and the units would be, you divide one by the other again, so it's been millimoles per decimeter cubed per minute. So millimoles per decimeter cubed per minute. So it's the same, so you divide one number by the other, you also divide one unit by the other. Standard form, you have to be able to convert from decimals to standard form. Standard form is the standard way of presenting a number in science, and in biology we often use minus numbers because we're dealing with small numbers a lot of the time. So in here we've got a 2.4 times 10 to the minus 9, so this is actually a very small number. It's a much easier to show the number like this than it is like this. So in this case, minus 9, so you move the decimal place 9 places to the left. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be the number that you have. That's the true number. This is the number in standard form. There's some other examples here. So this number is equivalent to 5 times 10 to the minus 3. So 5 times 10 to the minus 3 would be 1, 2, 3 decimal places to the left. So you have to be able to convert from one to the other. You don't want to lose marks for not using the correct number of significant figures. Sometimes it will simply say, show your answer to 3 significant figures, or use 1 decimal place. But in this question you can see that there are 2 significant figures here, and each of these values, well, most of these values are to 2 significant figures. These are to 2 significant figures, but these 2 are just to 1. So the vast majority of the data is to 2 significant figures, so it would be acceptable to use that. So the rate of gas production in centimetres cubed per gram per minute. So there's been during the first 40 minutes. So during the first 40 minutes there was 3.1 centimetres cubed of gas, and then you divide that by the number of minutes. So divided by 40 minutes. So 3.1 divided by 40 gives an answer of 0.7. However, should be 0.70 centimetres cubed per minute. Because this is now to two significant figures, and most of the data is also to two significant figures. You have to be able to compare and use mean, mode and median. So from this series of numbers, the mean, you add them up, divide by the number of samples, so that's quite straightforward. So you get a mean of 6.1. To calculate the mode, it's the most common number. You can see there's two lots of 8, there's only one of every other number, so 8 is the most common, and median's the middle number. So to do a median, you've got to place them in order. So we've ranked these numbers in order from 2 to 10, and there are 7 different numbers. The fourth number is the middle. You can see the 3 numbers either side of 7, so that is the middle number, so 7 is the median. There are advantages for doing different sorts. The mean is by far the most common one used in science. However, this is affected by outliers, but the big advantage is that it uses all of the data. So the mean uses all of the data, however the mode and median do not, because 8, you're only using that value, you're ignoring all the other numbers, and this one here, the middle value is 7, so you're ignoring all the numbers that side and all the numbers that side of the middle. So mean, usually the one's used because it uses all of the data. However, it is affected by outliers, and an outlier being a number that doesn't fit the pattern. You need to know how to spot correlation between variables, so this would be used on a scatter plot, scatter diagram. So here you can see there's definitely a positive correlation between the percentage of fat in the diet and the death rate from breast cancer. A negative correlation would be in the opposite direction. You can see though it's not a perfect correlation because not all the points are bang on the line. So a perfect correlation, every single point would be on the line. So there is a positive correlation, but it's not perfect. There is a standard answer for, is there a link between two variables? So the first answer would be, yes, there's positive correlation, which there is, but correlation does not mean that causation. So fatty diet does not cause breast cancer. And you can tell that for one reason, is because not all the points fit straight on the line. So this population here has eaten less fat, so more fat, but they've got less cases of cancer. So they've eaten more fat, but have less cases of cancer. So this indicates that in this case breast cancer could be due to another factor, so for example age. So that is a standard answer there. So these are 3 statistical tests that you need to know how to select which is the most appropriate. This will become much more clear next year with a lot of the topics that are done. However, you still could be asked this in your AS exam. So statistical tests are used to show different things. So the chi-squared test is used to see if there's a difference between observed and expected values. This is often used in genetics. So because of a genetic link, there should be a certain proportion of a population that has blue, brown or green eyes. So you can then compare, does the population you've got match the expected values. A student t-test allows you to compare the mean values of 2 sets of data. It's a very similar thing to using a standard deviation, those standard deviation bars to see if they overlap, but it's another step up. It's a more rigorous statistical test. So it allows you to show if there are differences, significant differences between mean values of 2 sets of data. A correlation coefficient is a way of showing if you've got significant correlation. If you've got significant positive correlation, you've got significant negative correlation. So a value of 1 indicates perfect positive correlation, -1 perfect negative correlation, and a value of 0 using Spearman's rank means there's no correlation at all. So this allows you to prove if the correlation is significant or not. You need to know about the probability value when, so this is linked to the statistical tests. So your probability value, if you see one this year, will be p, represented by p, and it's this value that you can use to see if the results are significant. So if a t-test shows a significant difference, and the value you've tested it to is p equals 0.05, then you can be 95% sure that the results are not due to chance. So you can be 95% sure you have got a significant difference. And even better significance, if p is equal to 0.01, so if your t-test is significant to this level of probability, then you can be 99% sure the results are not due to chance, 99% sure that you have got a significant difference. An even better value, if your p-value, if your t-test shows a significant difference to p is equal to 0.001, then you can be 99.9% sure the results are not due to chance. You can be 99.9% sure that there is a significant difference between two values. So the value of p shows to what extent you can be sure the results are not due to chance. Dispersion is a term that's used for the spread of the data. And there are two ways you can look at the spread of data. You can simply use the range, which is the difference between the highest and lowest value. A better method is standard deviation, which is a statistical test which shows the spread of data around the mean. One standard deviation either side of the mean represents 67% of the data. So the range is a lot quicker to use, but it is affected by outliers. So if one value is a lot higher than the vast majority of the data, your range will be really big, whereas standard deviation would not be affected by the outlier. So a range you cannot use to see if you've got a significant difference, but a standard deviation you can. So standard deviations can be used to say, yes, this mean is vastly different, has a significant difference than the other one, whereas you cannot use a range to show that. You could be asked a question to calculate the percentage error or the uncertainty of a measurement. So the uncertainty of a measurement, you have to look at the piece of equipment that was being used. It's quite likely that they would give you the uncertainty of a piece of equipment, then you just have to calculate this. But if you have to work out the uncertainty of a measurement first, in this example, each of these bars is 10 millilitres or 10 centimetres cubed. So the uncertainty is halfway between. So you've got plus or minus 5 centimetres cubed uncertainty, because you can't really be sure. When making the measurement, you've got a wobble room of about 5 centimetres cubed. So the uncertainty for this measuring cylinder is plus or minus 5 centimetres cubed. This measuring cylinder here, you've got 10 divisions between each. So, each division is 1 centimetre cubed. So halfway between each centimetre cubed is 0.5. So you've got plus or minus 0.5 as the uncertainty. So from both of these we measured 80 centimetres cubed. So we come up to here on this measuring cylinder, and it would come up to here on this measuring cylinder, measuring a volume of 80 centimetres cubed on both. So the calculation for percentage error is uncertainty divided by the amount measured times by 100. So the uncertainty of this piece of equipment is 5, because it was plus or minus 5, divided by the measurement you're taking, which is 80 times by 100. So the percentage error is 6.25%. So every measurement you take with this has a percentage error of 6.25%. With this piece of equipment, because it's more precise, because the subdivisions are much smaller, you've got a smaller percentage error. So the uncertainty is smaller, so it's 0.5. We've measured the same volume divided by 80 times by 100. So our percentage error is 0.625%. So this is one way that shows that if you've got more subdivisions, the piece of equipment is more precise because you've got a smaller percentage error. You could be asked to sketch or predict a linear relationship. So a linear relationship is a graph with a line, so it's either going up or it's going down. So a linear relationship is represented by this formula, y equals mx plus c, and m represents the gradient. So when doing a graph, you could have an example where you might say this is a line for a concentration of enzyme of 1. Predict or sketch what the line will look like if you double the concentration of enzyme, in which case your line will be steeper, the rate of reaction will be faster. So that's the kind of thing. If the m value is greater, then the line will be steeper. We've already covered calculating a rate of reaction in the biology videos, but you could be asked to use a tangent to measure rate of change or a tangent to measure the rate of reaction. You don't need to use a tangent if the line is straight. So you would not need to use a tangent for this 25-degree line at all because it's a straight line. So you could just read off the graph for that. However, if the line is curved, you have to draw a tangent. So to measure the initial rate of reaction, because this line is curving, you have to draw a tangent that matches the gradient. So the gradient at the start of that line, you then extrapolate that line, and you've then got points that you can read off. So rate is the change in y divided by the change in x. So the change in y divided by the change in x. So the difference in the y values between there, so you read off from this point, between there and there. So between there and there, so a value of 15. And the difference in x, so read off from that line, straight line. Now you've got a straight line, you can read off from that, and the difference between x is 60. So it's 15 divided by 60 gives a value of 0.25 grams per decimetre cubed per second. So it's grams per decimetre cubed per second. So you need to create a straight line, which you can then read off the difference in y divided by the difference in x. In this example, they asked you to work out the rate of reaction at 60 seconds. Again, you can't just read off the graph because it's a curved line. So the rate of reaction is getting less and less and less as time progresses because the line is getting less and less and less steep. So you have to do a tangent to line, so that the slope of that curve, you do a tangent that mirrors the slope of that curve. Really, that line should be touching, but it's hard to do on the computer. So the line that matches the gradient at 60 seconds, and then you can read off the difference in y. So the difference in y is between there and there, so a value of 10 between there and there. And the difference in x is between that point, so read off from the top of that line, and then read off the bottom there. So the difference between there and there is the difference in x. So 10 divided by 100 is 0.1 grams per decimetre cubed per second.